group is. A group is, well, lots of different kinds of groups. A group is some kind of algebraic system which fits this pattern here. Yeah? Got a set called G here in the definition. We've got some binary operation represented by asterisks or star there in the definition. The binary operation, something like plus, adding together numbers, multiplication, composition of functions, those kind of operations. Operations on a set of objects that take two arguments, an ordered pair, first one and the second one, combine them in some way to produce another one of the elements, another element of G. And a group is when the system obeys these certain basic algebraic properties. The system is closed under the operation, we've gone through that a few times. The operation is associative, just a basic algebraic property, which most interesting mathematical operations tend to be, I guess. And then existence of identity element and existence of inverses. So what we've been doing over the past few weeks is mostly just meeting lots of different examples of groups. Okay? So we looked at a dihedral symmetry group of a triangle. We looked last week at the modular arithmetic groups, where you have addition modulo n or multiplication modulo n. We did a little bit of kind of initial group theory last week as well, when we proved some basic consequences of the group axioms. Things like the identity element being unique and so on, inverses being unique. We've met the idea of a Cayley table, which is like an operation or a multiplication table for the group, okay, which you can produce for a group of manageable size. It's an operation table that shows you everything in the group. But today we're going to meet this new example of groups. They're very important in the whole of group theory, and these are called permutation groups. Okay? So this is the section we're going to look through today. And it's mostly just kind of meeting this new object, going through the definitions, and learning to use the new notation associated with it. So permutation group is something which is naturally associated to a subject in mathematics called combinatorics. Combinatorics is the name. It's a part of what you might call discrete mathematics, and it studies basically, as the name suggests, studies the possibilities of combinations of objects in a very general sense. It's very closely related, or it's kind of goes hand in hand with graph theory, which you've been doing. Some of you have been doing, might have met some of the basic concepts of that in GAN and the decision maths. So having a graph, a system of vertices and edges between them, and studying the mathematics of those structures. Okay, so a basic definition is, what is a permutation? Well, a permutation is a function, a kind of function, and we talk about a permutation on n symbols or n objects. So a permutation of the symbols 1 up to n is some function whose domain and codomain is that set of labels 1, 2, 3, 4. Sorry, I skipped out 3. I should have skipped out 3 there. Some set of n labels. And a permutation is any kind of a function from those labels to themselves, which is bijective. So 1 to 1 and on to 1 to 1 and on to. And what the group is, the symmetric group, so that's the name of it, the symmetric group. It's confusing, it's quite close to the term symmetry group. Symmetry group is a group of geometrical transformations, rotations, reflections, and so on, which are the symmetries of a particular object that you're focusing on. The symmetric group stands for, so the symmetric group with index n is the set of all permutations on n objects. So all bijective functions, set of elements 1 to n to themselves, under the operation of, well, the obvious operation when you've got functions there, under composition of the functions. Okay. So let's just look at some basic examples. Example permutation. So let's say we've got the elements 1, 2, 3, 4, 5. We've got them over here again, 1, 2, 3, 4, and 5. So this is the domain on the left, the codomain on the right. A permutation is a bijective mapping from the domain over to the codomain. So bijective means that, well, it's injective. So 2 to 4. It's injective and surjective. Okay. Now there's the same number of elements in the domain and codomain. And we never have two arrows arriving at the same image, because that would be non-injective. We have two elements in the domain getting sent to the same element in the codomain. So we never see that. And hence, because it's the same number, we never see an element in the codomain which isn't an image. Those are the two aspects of being bijective. I'm going to name this permutation sigma. Small Greek letters are traditionally used for representing permutations, or quite a lot of the time. So here's one permutation sigma. This is a permutation sigma, which is an element of S5, we could say. It's a permutation of 5 objects. Now, in all of this, when we're talking about permutations, the numbers we're using, they're just labels. So we're never going to be, we're never going to be adding these numbers together or multiplying them. We're not. They are just purely used as labels. Equally well, we could talk about A, B, C, D, E here. We're just looking at how we study or how we gather together all possible permutations of a collection of objects. Okay. Now, so let's start to see the idea of composition. See, equally well, I could put down another copy of the set here, 1, 2, 3, 4, 5, and I could draw another permutation. And 2 to 3, 3 to 2, 5 to 4, 4 to 5. So this one I'm going to call tau. So the permutation sigma and tau. Okay. The composition of them, which we'll write as tau after sigma. How do we, what's the permutation tau after sigma? It's the composition of these two. This is some pretty simple stuff, but there's no hard calculations involved here. It's just getting some definitions straight and some notations. So what's the composition of them? When you compose two functions, you're feeding the output of the first function, which is here sigma, into the input of the second function, which is tau. And then you're looking at the overall function. Well, that's the overall mapping diagram that we see here when we just, get rid of those labels in the middle and just look what happens when you go from left to right, from the far left to the right. Okay? So 1 goes to 2, but then 2 goes to 3. So in total, 1 goes to 3. 2 goes to 4, but then 4 goes to 5. So in total, 2 goes to 5. 3 goes to 1, and 1 goes to 1 under tau. So in total, 3 goes to 1. 4 goes to 3, and 3 goes to 2. So in total, 4 goes to 2. And lastly, 5 goes to 5, which then goes to 4. Okay, so that's the diagram, that's the mapping diagram for the composition tau after sigma. Sigma after tau. Sigma after tau isn't so easy to read off because of the way we've got them written up here. So if we apply tau first and then sigma, well, tau sends 1 to 1, but sigma sends 1 to 2, so in total 1 goes to 2. Tau sends 2 to 3, but sigma sends 3 to 1, so in total 2 goes to 1. Tau sends 3 to 2, and sigma sends 2 to 4, so it goes 3 to 4. Tau sends 4 to 5, and sigma sends 5 to 5, so in total 4 goes to 5. Where does 5 go? Well, it has to go to 3. Go to the left. But just check, 5 goes to 4 under tau, and then sigma sends 4 to 3. So yeah, in total 5 goes to 3. And of course, as is usual behavior for composition of functions, when you compose them in the two orders, if you even can, if the domains and codomains line up, but we see different functions there. So tau after sigma is not the same function as sigma after tau. They're different functions. They're different functions because they do different things to the arguments. They have different values. This function sends 1 to 3, this one sends 1 to 2. So they're clearly different functions, clearly different permutations. So, you see our first theorem there. It's a bit of a grand name, but it's a fairly quick theorem to prove. How big is the group of all permutations on n objects? Well, gives the answer there. It's n factorial. So that question is, how many? You just look at that permutation sigma. How many different ways could I complete this mapping diagram? Well, see how many, this is the proof of this, if you like. How many permutations sigma in S5, let's say, are there? Question mark. Well, you kind of think about the choices you go through when you're constructing them. So to construct a sigma by assigning values to sigma 1 up as far as sigma 5, that's what you'd have to do to construct a permutation sigma. It's 5 possible arguments to the function, 1 to 5. You'd have to make choices. And how many choices are there for the element sigma 1? Sigma of 1? 5 choices. 5 choices for sigma 1. Now, having made a choice, having made an assignment for sigma 1, how many choices for sigma 2? 4. There's 1 less. Why is there 1 less?
1 has already taken up 1.
1 has already been taken up, and what stops us from using that element again? Exactly. See, once I choose to make 2 the value of sigma 1, I can't send anything else to 2, because that would break the injectivity, the injective property of the function. So the function has to be 1 to 1. So once you assign a value, that can't be assigned to any of the other arguments. Okay? So 5 choices for sigma 1, and then there are 4 choices for sigma 2. Many choices for sigma 3? 3, because there's only 3 elements left that haven't been assigned. You keep going. Okay. So 3 choices for sigma 3. 2 for sigma 2. And your last assignment,
Sigma 4.
oh yeah, sigma 4, yeah. For sigma 5, there's only 1 element remaining, no choices for sigma 5. No choice, one element to choose from, so effectively it's determined. Only 1 choice, only 1 possibility for now, all of these changes are independent. You can have any combination of these changes. So 5 choices for the first option, and any of those 5 you can choose. You've got 4 different choices for the next element. So we have to multiply together these options. It's like a branching choice tree. Okay. But in total, we multiply together these number of choices. So 5 by 4 by 3 by 2 by 1, which is equal to 5 factorial different sigmas in S5. And there's nothing special about 5 here. You run exactly the same argument for any n. So in general, Sn has n factorial elements in it. So it's very easy to understand how big these groups are. Okay? And they're quite big. How many different permutations of 100 objects? How many different ways of rearranging 100 objects in a line? Is 100 factorial, which is a huge number. Any questions so far? Now, on the one hand, permutation groups might look kind of simple when we look at them, but really they're quite complicated. I mean, I might give the argument today, but probably next week. There's a sense in which permutation groups and subgroups of them. So there's a natural idea, okay, we haven't formally defined it, but you can think of the natural idea that a large group could have subgroups within it. Little subsets of the large group that act like little groups themselves under the operation that's going on in the group. So it's the same way you have vector subspaces. A little subspace within a larger one with respect to the same operations, which is a closed system with respect to those operations. Exactly the same way you've got subgroups. So inside a large group, you can have smaller groups. Well, it turns out that permutation groups and subgroup, these symmetric groups and subgroups of them, they can represent any finite group at all. Okay, so any finite group that you might come across, whether it be the symmetry groups of geometrical objects, whether they be these modular arithmetic groups, or group matrices, any of these wild and wonderful and lots of things we haven't even touched upon, examples of groups. As long as they're finite, in a sense, they can be represented by some kind of permutation group. Right? So there's a sense in which, really, when you're looking at these, when you're considering these permutation groups, really we're considering all groups. Okay? So there's whatever amount of complexity there is in groups in general, it's also contained in permutation groups. We'll make that notion a lot more precise in a couple of lectures' time to do with isomorphisms, mappings between groups and so on. But for now, so having said that, having kind of made those remarks that permutation groups are, contain all of finite group theory within them, so to speak, let's do some more basic stuff and introduce some notation that we can use. Now these mapping diagrams I've just drawn are great. They're very clear, they're very instructive, they show you exactly what's going on, but they take up a lot of room on the page, they're a bit laborious to draw. Once you can start considering lots of permutations, it quickly becomes a little bit too cumbersome. So we'd like to have more compact notation for permutation. So there's the two-line permutation, two-line notation for permutations. Well, it's easiest just to throw out some examples. Okay, there's an example sigma mentioned in the notes, but I'm going to just work with the sigma that I put down on my page. So that very same, if you copy down that sigma precisely, so that sigma there. So for example, the earlier sigma and tau are denoted. So here's the two-line notation for sigma. It's two lines of symbols, and it's basically just all the essential data from the mapping diagram. So the arguments to the function go across the top, and underneath them you put the corresponding values. So Nice and simple. So 1 went to 2, 2 went to 4, 3 went to 1, 4 went to 3, and 5 went to 5. So that's the two-line notation. So effectively, the mapping diagram just turns sideways, and you just follow the arrows. Yeah. And tau, permutation of 5 symbols. So there's the 5 arguments, and what does tau do? Sends 1 to 1, 2 to 3, 3 to 2, 4 to 5, 5. Nice and easy. Yeah. Okay, we've dispensed with all the arrows. Really, we don't need the arrows. We just need the associations between the arguments and values. And we can use these to obtain compositions as before. So e.g., let's try and do tau after sigma. I know we worked it out before, but let's do it again. So here's tau on the left, 1, 2, 3, 4, 5, 1, 3, 2, 5, 4. Here's sigma, 2, 3, 4, 5, 2, 4, 1, 3, 5. And to compose them, what is the single two-line notation that stands for the composition? We just had to compose them. Now remember, in this tau after sigma, so sigma goes first, which is this one here. Tau, sigma. So sigma goes first, sigma sends 1 to 2, tau sends 2 to 3. So total 1 is 3. Sigma sends 2 to 4, tau sends 4 to 5. See, sigma sends 3 to 1. 1 is the intermediate value. That gets passed to tau. 1 gets sent to 1. So 1 is the final value. Sigma sends 4 to 3. Tau sends 3 to 2. So 2 is the final value of 4. Sigma sends 5 to 5. So 5 is the intermediate value. And tau sends 5 to 4. So total composition. Tau after sigma has that two-line notation. So that should tally exactly with the mapping diagram we drew earlier. Just that one there. Was it? Sorry, this one over here. Tau after sigma. So this two-line notation here should exactly match that. This mapping diagram here on the left. 1 goes to 3, 2 goes to 5, 3 goes to 1, 4 goes to 2, 5 goes to 4. Okay. Nothing too startling. Nothing too startling up to now. Turns out, however, that even this two-line notation is still a bit redundant. You'll notice in all of these two-line notations, I've always put 1, 2, 3, 4, 5 across the top. So effectively, I'm wasting my time. If two-line notations always have 1, 2, 3, 4, 5 across the top, really, I'm wasting my time writing that out. Maybe we can compactify it a bit more. We can. So the second kind of notation, so that was the two-line notation. It's better than the mapping diagram. We're not wasting our time drawing arrows, but we're still wasting our time a bit by putting down arguments and values. Now we could just agree to write, to just dispense with writing the arguments and just say, well, tau after sigma is this sequence here, 3, 5, 1, 2, 4. As long as we understand that we're talking about these at the back, this is the image of 1, that's the image of 2, 3, etc. We don't do it that way though. We do something else which relies on some of the structure that is in permutations. This isn't something we've picked up on yet, but we'll emphasize it now. Okay? So a better type of notation, which is cycle notation. Now, before we look at cycle notation, let's think about the idea of cycles. So within any permutation, there is structure inside it. Okay? So example, consider this permutation from S8. symmetric group S8. So I'm going to give it 2-line version. 1, 2, 3, 4, 5, 6, 7, 8. The arguments, and it's 7, 1, 8, 3, 5, 6, 2, 4. Okay, that's perfectly good permutation from S8. 8 objects rearranged. So mapping from 1 to 8 to set 1 to 8. But there's actually kind of some structure going on there, which is kind of, well, it's not really geometric structure, but it is kind of visual structure, and it helps if you draw a picture. So to see this, to see what I'm going for here, which is the cycles within the permutation, let's just throw down the elements 1, 2, 8 in just some random order on the page. Remember, these are just 8 different objects, labels for objects. There's no inherent meaning in the order 1, 2, 3, 4, 5, 6, 7, 8. Just talking about 8 different objects. And this, what I'm going to do is draw the mapping diagram again. But this time, see, before when I drew mapping diagrams, I used, the domain was over here and the codomain was over there. I had a separate domain from the codomain. But of course, these are the same sets. The domain and codomain is just the set of labels 1 to 8. So I'm just going to use the same set of labels for the domain and the codomain. I'm just going to draw arrows around. So let's start at the beginning. 1 goes to 7. Okay, so 1 gets sent to 7. Now, but instead of looking where 2 goes, I'll continue from where I am. See, I've arrived at 7. Well, what does the permutation do to 7? 7 it sends to 2. That's fine. What does it do to 2? 2 it sends to 1. That's kind of interesting. I'm back where I started. What this shows is that within this permutation there exists this little cycle of 3 elements, which naturally go together. Then I'll use a different color and I'll start somewhere else. And just emphasize there's no meaning to the numbers. Let's just start at 5. So I know 3 is the smallest one I haven't used, but let's just start at 5. 5 goes to 5. Oh, well, that was short and sweet. 5 just goes to 5. It's its own little cycle of length 1. Somewhere else, 4. 4 goes to 3. Where does 3 go to? 3 goes to 8. Where does 8 go to? 8 goes to 4. 6 is out here on its own again. 6 goes to 6. So, in a very natural way, any permutation decomposes into cycles. It just kind of happens naturally. You start off at any element, you start tracking where, so we started at 1, 1 got sent to 7 by this permutation. Where does 7 get sent to? It gets sent to 2. Where does 2 get sent to? Well, 2 gets sent up to 1. That's cycles. So we got 2 cycles of length 3 and 2 cycles of length 1. Let's give this one a name. Let's call this mu. So nothing about that was forced. That wasn't forced or artificial. It just kind of naturally happened. So mu naturally decomposes into a collection of, now call them disjoint cycles. You remember what disjoint means? You met that in set theory with Said. Disjoint sets are sets which have no intersection, empty intersection, sets of completely different objects. And these cycles, the way they naturally happen is they're all disjoint. So the cycle where 2 lives is completely different to the cycle where 4 lives. I mean, if there was any intersection, they'd be parts of the same cycle. Actually, disjoint cycle. These cycles are denoted, so this is the cycle notation now. See, this cycle here, you have to get the order correct, so it goes 3, 8, 4. 3, 8, 4 is the notation for the black cycle there. Black. The blue cycle is 7, 2, 1. And then you've got these two trivial cycles of length 1, 5, and 6. So these are examples of cycle notation. Now they're formally defined there on page 67, definition 5.18. So you see, it's no longer a two-line notation with separate lines for arguments and values. We're using the same collection of symbols for arguments and values. So when you're reading this cycle here, it says that 3 gets sent to 8 under this cycle, under this permutation. 8 gets sent to 4, 4 gets sent to 3. So each one gets sent to the next one on to the right, and the last one gets sent back to the first one. Okay. So equally well, this cycle could be written 4, 3, 8, or 8, 4, 3. They're different cycle symbols, but they're referring to the same cycle. It's just the same bunch of elements traversed in the same order. Of course, it is not the same cycle as 8, 3, 4. Important to get this point. So that red cycle, 8 to 4 to 3, to 8 to 4 to 3, to 8 to 4 to 3. The first three symbols there all refer to that same permutation. But this one is different, because this one goes through the elements in a different order. This one goes 8 to 3 to 4, which is different. So the location at which you start in your cycle symbol is not important. These are just arbitrary labels for objects. But the cyclic order is important. If you change the cyclic order, you're talking about a different cycle, different permutation. So these are our different cycles. And we then denote a permutation, or the permutation mu, as a composition or a product. Product, just to use the general term for the binary operation in the group, of its disjoint cycles. So mu, I can write mu is 3, 8, 4, 7, 2, 1, 5, 6. So that's this so this permutation, we drew the diagram up there, the mapping diagram up there. I use different colors. The different colors don't come out amazingly in the overhead. That's the idea. Naturally decomposes into different cycles. Each of the cycles can be denoted by a cycle notation, and then you just whack all the different cycles down, and you get your notation for your permutation mu as a product, a composition of disjoint cycles. Now, the operation that's taking place here is still composition. However, because these cycles are disjoint, it doesn't matter in what order we apply them. See, if you want to apply the operation mu, send everything to its image under mu, it doesn't matter whether you send 1 to 7 first, and then 7 to 2, and then 2 to 1. If you apply this cycle first, and then go and apply this cycle, because the cycles are disjoint, they don't interfere with each other. So that means, actually, disjoint cycles commute. you can change, you can flip their position. So equally well, this is equal to this. So we note that disjoint cycles commute. You can change the order that they appear in the composition, because they don't interfere with the images and values of each other, because they are operating on a completely disjoint sets. Also, by convention, we don't have to include cycles of length 1. By convention, if a cycle, so these individual things are cycles, if a cycle does not mention a label, we understand that that cycle leaves the label fixed. It doesn't do anything to that label. And what that allows us to do is to drop the cycles of length 1. So we can show mu as the product simply 721 with 384. So once we know that we're talking about a permutation from S8, that's the most compact form of notation for mu. It's just composed of 2 disjoint cycles, cycle 721 and 384. Now you then might ask them, well, what does mu do to 5? And what does mu do to 6? Well, by convention, because 5 and 6 are not mentioned anywhere, it's implicitly understood that they are fixed by mu. So 5 gets sent to 5 and 6 gets sent to 6. Okay. So what this notation has done is it has compactified things quite a bit, because if you look at the 2-line notation that we started off with for mu, there at the top, we had 16 different symbols, 2 big brackets, and it took up a double height, so it interferes with the proper layout of text on a page. Whereas now we've got it down to just this nice symbol now. Just using 6 labels, it turns out, for this mu. And just small brackets, it's the same height as the surrounding text. So just aesthetically, it's quite a good notation. It's compact, it only contains the essential information, but the information that it does contain is, it shows you something very structural and inherent to the permutation. So this permutation mu, it just naturally breaks apart into these disjoint cycles. And you see that immediately in the cycle notation. Now, what we want to be able to do is to get to grips with composing permutations using their cycle notations. So you need to get comfortable with composing, not necessarily disjoint cycles, but composing arbitrary cycles. For example, so this is example 5.9. Yeah, see there's a few examples in 5.9. Look at number 1. So number 1 sets us this exercise, so 1, 3, 2, 4, 5, 2, 3, 5. Okay, we've only mentioned 1 to 5, so this could be a permutation in S5. Permutation on 5 symbols, although it could be a permutation on any number of symbols. The symbols that aren't mentioned there just get fixed. Well, you notice here now, it's a product of cycles, a composition of cycles, but the cycles aren't disjoint. 2 is mentioned in a couple of them, 3 is mentioned in a couple of them, 5 is mentioned in couple. So they aren't disjoint cycles. So they're different disjoint cycles, and we're going to compose them in this order. And what we're going to lay down is we're going to try and build or construct the disjoint cycle composition of them. So to emphasize that, the numerical order is no importance, I'm going to start at 4. Just because 4 is my favorite. So I'm going to start building this. I'm going to start building the disjoint cycles of the compositions. So where does 4 get sent to by this product? Remember, it's a composition of functions, so this is the one that's applied first. What does this cycle do to 4? It leaves it fixed because it doesn't mention 4. So this cycle sends 4 to 4. So 4 is the intermediate value that gets passed on to the middle cycle. What does that cycle do to 4? Sends it to 5. So 5 is the intermediate value. That gets passed on to the last function. What does that last function, that last permutation do to 5? Sends it to 5 again because it doesn't mention it. So in total, 4 got sent to 5. You feed 4 in at the front. This leaves it fixed. This sends, so 4 is the intermediate value. 4 gets sent to 5. 5 is the intermediate value. 5 remains at 5 now. So in total, 4 gets sent to 5. So that's the beginning of the first disjoint cycle in this product. We then just seek to continue it. So we ask ourselves, what happens to 5? What does this first one do to 5? 2. 5 gets sent to 2. What does this one do to the intermediate value of 2? 4. So 4 is the intermediate value. What does that one do to 4? No. Leaves it at 4. So what do I put down here? Do I put down 2? What do I do instead? Just close the bracket. Because this is the end of this disjoint cycle. This product sends 4 to 5 and 5 to 4. So we've discovered that within this, whatever this permutation is, the product of these, within it, there's this little 2 cycle. 4 gets sent to 5 and 5 gets sent to 4. So there must be some more information in it. Now let's begin at 1, say. What happens to 1? Goes to 3. See, 1 is left fixed, still left fixed, and 1 gets sent to 3. What happens to 3? Total? 2. 3 gets sent to 5. 5 gets sent to 2. 2 is left fixed. So 3 gets sent to 2. Then what happens to 2? Two goes to 1. 2 gets sent to 3 by the first one. 3 remains fixed, but then 3 gets sent to 1. So 2 gets sent to 1, so that's the closing of that cycle. Are there any other symbols that were mentioned in the previous one that we haven't accounted for? No. So they've all been accounted for. So this is the answer. This is just an arbitrary product of different cycles. They're not disjoint, but by extracting out the disjoint cycles of it, we see the kind of fundamental structure of the permutation. So on these 5 symbols, it's sending 4 to 5 and 5 to 4. That's one cycle. And then it's going 1, 3, 2. Of course, you might have some other elements. Maybe this is in S8. What are the cycles involving 6, 7, and 8 that might be here? They're just these little trivial 1 cycles. 6 is left 6, 7 is left 7, and 8 is left. There's an ambiguity here about exactly what permutation you're talking about. What is the exact domain? I mean, we know from the cycle notation that it only does something non-trivial to the labels 1 to 5. Any other labels that there might be hanging around just get sent to themselves. Okay, we got through some good stuff. That's what I wanted to get through. call that notation. So next week we'll do some further investigations of this, and I'll show you I should get to this next week. I'll show you the proof of why these permutation groups really represent all possible finite groups.